Welcome back, students. Today we're going to be continuing with section 6.6, which is talking about variation in general. Today we're going to be talking about a more specific type of variation, which is inverse variation. So the general idea of inverse variation is as one variable increases, the other variable decreases. Okay, so just as direct variation was as one increases, the other increases, as one decreases, the other decreases, that was with direct variation, we are going to be doing the exact opposite, the inverse of that. So y varies inversely as x has this relationship, y equals k over x. My x needs some work. This is just saying there's some constant k. It could be any number. And then x needs to be in the denominator, okay? So let's designate that. Let's change the color of the y here to blue. Let's change the k to purple, just so you can see that k absolutely needs to be in the denominator. Sometimes you will see it written, and I'll do a video on this with the Khan Academies, but sometimes you'll see it written like this, and it'll say, is this direct variation? And it is direct variation. They'll ask if this is inverse or direct variation. And this is inverse variation because once you solve for k by dividing both sides by x, you'll see that y equals k over x. So don't be fooled in thinking that something written like this is not inverse variation, because it in fact is, okay? So let's keep that in mind. The other thing that you will see, the other form that you will see sometimes is y varies inversely as the nth power of x. You'll see this often with problems involving gravity or any sort of acceleration. And the only difference with this is you have to raise x to the nth power. So it's still in the denominator, but the only difference is because it says nth power here, that's why the x is raised to the nth power there. So we don't have any examples over the nth power, but I hope you guys see that the formula it's essentially the same. You just have to raise x to the nth power. So let's go over an example involving inverse variation. Arlene is driving to her friend's house in West Palm Beach. The distance is 70 miles. Hint, distance equals rate times time. So we're going to be using this. Distance equals rate times time. What will Arlene's average speed be if she completes the trip in 60 minutes? Okay, so 60 minutes is our input here. So what we're going to do is we're going to go ahead and we are going to input. So we're looking for speed. Speed is the rate. Okay, so the first thing we should probably do before even inputting 60 minutes in for time is we need to get the rate by itself. If that's what we're solving for, then that's what we should get by itself. So let me rewrite this equation. D equals, let me make it blue just so you can see it's different, R times T. So now we are going to divide both sides by T. Keep changing the wrong color here. Divided by T. And now I know that R equals D over T. In this case, the distance is 70 miles. There's no changing it. Okay, it's going to be 70 miles. That's the constant. This is the constant variation. It's not going to change. It's always going to be 70 miles. So that's a way to think about this K, is it will not change. There's no input or output. It's just 70 miles. It is what it is. That distance is 70 miles, and it's not changing, okay? But we do know that this 60 minutes can be inputted, and this 60 minutes goes in for time, okay? So what we're going to do is we're going to put in both these values. We're going to put in 60 minutes for time, and we're going to put in 70 miles for the distance, 70. So now it's just a matter of calculating our distance. So we could either leave it as a fraction, or we could convert it to a decimal. So our rate is going to equal 7 over 6 miles per minute. Okay, now no one ever uses that. So what you should probably do is you should probably change minutes to hours. So we know that it's 1 hour. And then we can just go ahead and leave it as rate equals 70 miles per hour. And that's generally what we're going to use. I mean, obviously no one talks about how fast they go down the road per minute. Okay, so now let's think about this problem. If Arlene's time increases, what happens to her average speed? Okay, so as her time goes up, so R equals 70 over. Now think about if she had done 2 hours. Does that increase or decrease her speed? Well, that would become 35 miles per hour. So her average speed would go down. Okay, so as her time increases, as she takes longer to get there, obviously her speed goes down. She has to move slower if she's going to take more time going this constant distance right here, 70 miles. Okay, on the other hand, if her speed decreases or her time decreases, so instead of 2 hours, let's say she takes 0.5 hours. Well, now that means she has to go 140 miles per hour, and I don't know what kind of car she's driving to go that fast, but that would mean that her average speed needs to increase. So I hope you guys see that this is an inverse relationship here. Okay, so her speed is an inverse relationship because as her time goes up, her speed goes down, and as her time goes down, her speed goes up. Let's go to the last section here. If Arlene wants to average 75 miles per hour, in how much time must she complete the trip? So now we're inputting this in for R. We still know that our constant D is 70 miles. And now we're going to be solving for T time. That's our unknown. So let's go ahead and put this in. Well, actually, again, before we do that, we should probably solve this in terms of time, because that's what we're going to be solving for. So D equals RT. We're going to solve for T. So now we have D over R, the distance divided by the speed, is equal to the time. Let's go ahead and input these values. I'll just go ahead and I'll use orange this time. So we have 70 miles divided by our rate, which is 75, and that equals our time. So let's go ahead and you could either reduce this as a fraction or you could use a decimal. I think a decimal in this case just is a little bit more clear. So the time equals 0.93 hours. I like if no one ever talks about it in that way, so I'm going to times this by 60 minutes. So I times this by 60 minutes in an hour, and I can convert it to minutes, which is 56 minutes, and that's my time. So she needs to cut off, if she wants to average 75 miles an hour, she needs to cut 4 minutes off her time. Or if she wants to cut 4 minutes off her time, she needs to increase her speed from 70 miles an hour to 75 miles an hour. So joint variation. This is when you have multiple variables involved. So for example, y equals, in this case we normally have kx, but now we can also put a z in there. So zkx. So now you have multiple constants that are affecting the input, which in this case the input is x, okay, and the output is y. Y is the output. Okay, so that's joint variation. One of the most practical uses of joint variation is interest problems, because there's multiple things affecting your interest and the amount of money that you get when you put something into a bank or you have a loan or something like that. So the interest on investment is given by the formula I equals PRT, where P is the principal, R is the interest rate, and T is time. If an investment earns $100 at 5% for 2 years, how much interest will the same principal earn at 4.5% for 3 years? So the first thing we have to do is we have to calculate all this for the original 2 years. So the principal says if an investment earns $100, so that is the investment is the earnings is there. Okay, so I is the earnings. This is the rate. That stays constant. Now, the principal is what we're not given. Okay, and then the other input we're given is 2 years. Now, this is the thing that can change. So that's technically our input right here. These other ones are constant. Okay, so that's just something to keep in mind. So and actually the other thing that can change is the P. That can change also. So that's why there's joint variation. There's multiple things that can vary within the same problem. The only one that's constant is this R. Okay. So now, how much interest will the same principal earn at 4.5% for 3 years? So let's go ahead and put in our formula. I equals PRT. We need to solve for how much money was put in initially. So $100 was our interest. 0.05 was our rate. We are looking for P. We don't know what our initial amount was, but we do know that it was put in for, let me just make it blue, 2 years. So we're just going to solve for P, so we're going to divide both sides by this product, which is 2 times 0.05, I believe is 0.1. So we're going to divide both sides by 0.1. So we do 100 divided by 0.1, that should give me 1,000. So we have 1,000 equals P. Okay, and essentially, for those that got lost in my speed, all I'm doing is solving for P here. Okay. Now what I'm doing is I'm just taking this principal and I'm inputting it into the second one. Okay, because now I'm solving for I instead of P. So now I have I equals my principal 1,000 times 0.045 times 3. Multiply all this together, 1,000 times 0.045 times 3, and I get $135. So with a little bit less of an interest rate, but a little bit more time, you get a little bit more money on your interest. So instead of $100, you got $135. Hope this helps you understand what inverse variation and joint variation are, and I'll see you next time.